Hello everybody and welcome back to another video. So today we're going to be continuing our journey through the HackTheBox Introduction to Binary Exploitation track. We've done 6 videos already and this one is going to be a continuation, but it's not going to build upon the last one. So this is kind of a different kind of exploit, so watching the last ones is not a prerequisite. However, it's very useful because it's general knowledge that might come in handy. So let's take a look at this challenge. So this is the Leet test challenge. And the description is, are we Leet enough? Are we Leet enough to pound this challenge and to get the flag? So without further ado, let's get started with this challenge. So obviously we first do file on our binary, and we see that it's an ELF binary, 64-bit, and it hasn't been stripped. Cool. If we do a checked sec on our file, we see that NX is enabled, and that's the only protection that is set. So what's next? Well, let's maybe check out the binary by running it, seeing what is this binary, what does it do. So let's run Leet test. It says, welcome to HackTheBox, please enter your name. So I'm Pink Draconian. And then enters, hello Pink Draconian, sorry you are not Leet enough, please come back later. And we then get the chance to enter our name again, and again and again. So that's the binary, really short, really quick. Let's see what's behind this. What is the code that's behind this? What's the assembly? And to do that, we're gonna use ghidra, obviously, because ghidra can give us a really nice decompilation of this binary. So we see that there's only one function, the main function. And if we look at that function, we notice that it starts by opening def urandom. Now that is on Linux a location where you can get random bytes from. So if I do, for example, head def urandom, we'll see that we get a whole lot of random bytes printed out to the screen. So we're going to get some random bytes, probably, because we're opening this file, and then we're reading 4 bytes from that file into our local 13 variable here. We're then going to do an AND operation on those random bytes that we got with FFFF. So this AND operation, what's the result of that going to be? Well, let's quickly go into Paint, because let's say that the random bytes that we got were 4 times. So these are our random bytes, and we're then going to do an AND with FFFF. Now, before FFFF, we can imagine zeros. And after our AND operation, obviously, for AND, you have to look at bits, and the bits have to be on the bottom, on the top, and the bottom have to be 1 both. So, for example, for these zeros, none of them, their bits are going to be 1. So the results of these first 2 bytes are obviously going to be 0. Then with the FF, FF is 8 1-bits. So this is just going to get the result from the other ones. So that's just going to be 3333. So after that operation, we see that we just have 2 random bytes left. So that's pretty much what that operation is going to do. And that's all we really need to know about it. So by the end of getting to this while loop, we have 2 random bytes. We see that this while loop is set with a condition of true. So we're going to keep on looping this while loop until we hit a break statement. It's going to print out, welcome to HackTheBox, please enter your name. We're going to get an opportunity, we're going to get 256 bytes to enter our name, and we're going to put that in this buffer that is 280 bytes long, so we don't have a buffer overflow here. It's then going to print out hello, and then it's going to print f our name or our input to the screen. Then it's going to check if those 2 random bytes that we had earlier times Leet code is equal to winner. And winner in this case is, I don't know if you can read this, but this says Cafe Babe, so CAFEBABE. So if that is the case, then we're going to break out of this while loop. If not, then it's going to say, sorry, you aren't Leet enough. If we break out of this while loop, we're going to open flag.txt, and we're going to print that out. So that's obviously what we want. We want to pass this if condition. But something that we notice right away is we only have the input of our name, and our name is not used in this condition anywhere. So what does our name do in this case? What is the point of it? Well, something that you might have already noticed is in this printf, our input is used as the format part. So printf exists out of two parts. First, you have the first variable that's going to be a format string, which is going to contain special characters, special formatters, such as here at the bottom. You can see another printf. And here they use %s, and then the second parameter is local 130. So what is going to happen when we run this? This is going to print out come right in. It's then going to fill out local 130 as a string here and print that out. So that's what a formatter string is. However, here our input is used as that first argument to printf, and that should never happen because that is a very big vulnerability, and we are now going to show how that is vulnerable and how you might exploit that. So let's get into that. So we have a printf where we control the format string. What does that mean? Well, we can pass in a formatter such as %s. %s is then going to look at an argument that is a pointer. It's going to take the string that that pointer points to and print that out. So what happens if we supply that in our binary? So if we run the test and we say %s, we see some weird things here. Hello to HackTheBox. Please enter your name, you aren't lead enough. So weird things happen. What do I assume happens here? Well, our first argument was hello to HackTheBox, please enter your name. So that is printed out again here. So okay, very interesting already. We can print some things out. If we enter more, we see we have some nulls here now, so weird stuff. But we don't really have a leak or anything useful. But luckily, printf has way more formatters. You can look at the man page to get a list of all of them. And for example here, the n one is very useful because the n formatter says that the number of characters written so far is stored in an argument. So if we have already written 20 characters, and then we have a %n, then, and I'm going to show you this as well on Paint, so we have 1, 2, 3, %n, and a pointer, which points to a location. So once we get to this %n, 1, 2, 3 have already been written out. So n is 3, so we're going to write 3 to this location. And that way we can write using printf. Why is that so peculiar? Well, earlier I said that our name that is inputted has no way of influencing this condition. Well, now that we are able to write to pointers, that might not be true anymore. Because what if we overwrite winner with something else that we can choose? So that way we influence this equation and we might be able to pass through and open flag.txt and get the flag. However, there's one issue with that. In order for this to work, we would have to have this pointer pointing to that winner location. However, we don't have a way of passing in pointers. So because we only control this first argument, so that is a bummer. We cannot use that. However, there's still way more possible arguments that possible formatters that printf can take. So looking at the other ones, we have, for example, %p. %p says the pointer argument is printed in hexadecimal. So what does that mean? Well, we obviously have a pointer, an argument that we don't control. That is something from the stack, something from somewhere. Because obviously your arguments, they start, the first argument is going to be, I think, the RDI register, and moving on with more registers. But if you have like 30 arguments, there's obviously not enough registers for that. So it's going to take stack locations as arguments. So with this p, we're going to print that out as a hexadecimal. So we might be able to leak some things from the stack or from somewhere else. So let's try that out. If we pass in %p, we see we get this very high address, which might be the stack. We can pass in more p's, so let me quickly copy that so we can paste that real quickly. And we can do a whole lot, and that way get a whole range of different numbers and things get out of this. Very interesting. So we can leak some locations here. Now, some of these are from the stack, and we can already see a recurring pattern in these here. We see 70, 25, 70, 25, 20, 70, 25, 20, 70, 25, 20. Interesting, because we also have a recurring pattern here. So, because our input is being put in this buffer here, which is on the stack, and we are printing out things from the stack, we might actually be able to get to our own input there. So let's see if that works. So if we print out like 8 A's, I think that's 8, and then we print out a whole bunch of percentage P's, we will see that here we see 61, 61, 61, 61, 8 times, and 61 is obviously the hex code for A. So we can actually print out our own input here, and that's going to be used as a pointer into our printf. So we actually have a way of controlling the pointer now. Now I'm going to make this a little easier on us because now we have all of these percentage B's and a lot of junk here. Let's count where this 6161 comes. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's a 10th one. So now we can do 8 A's again. And then we can say percentage P, but not percentage P. We're going to say percentage 10 $P. And that's going to take the 10th argument, and those are our A's here. So cool. What if we now use that with our as the pointer to write to? So what if we can now control one of these arguments. We want to use that in combination with this $sign, the percentage sign n, to overwrite that winner number, that winner integer that is stored, so we can pass the condition and get the flag. For that, we first need to figure out if that is really possible. So to do that, our first thing that we enter as a name should be the pointer that we want to use as an argument. So for that, I wrote a really quick script here. So we're going to start the process here. We have the winner function that I got from ghidra, so not the winner function, sorry, the location of this winner in memory. So that's 404078. So I put that in. Our payload is then going to be this winner packed, followed by percentage 10 $P. So we're just going to print that out again. We're then going to send that after our payload. Okay, let's see if that works. So if I run solve.py, we see hello x at sorry you aren't lead enough. And this x at might be confusing, because what is that? But it's very logical if you look at it, because if we go back to this location, 78 is the hex code for x, and 40 is the hex code for at, so x at is being printed out. So that's perfect. We have our location that we want to influence, or that we want to change on the stack, as a parameter, as an argument to our printf. And that's what we needed to use this percentage n that we were talking about earlier to write the number of bytes that have already been written out to that location. So let's see if we can actually do that. So I'm going to rip out this payload and start again. And this time what I want to do is I want to start out with saying, well, I'm going to have, for example, 3 spaces here, or let's start with 4. 4 places, and we're going to then start with percentage 10 $n. So this is going to, $n is going to take the amount of bytes that have already been written, which is 1, 2, 3, 4. And is then going to write 4 into the pointer that the 10th argument is pointing to. And we know that the 10th argument is the beginning of our payload string. So following that, we are going to write P64 winner, because we want to write 4 to this location where winner is stored. So let's try to run that and see what happens. And we see we get an end of file. Why this end of file? Well, first of all, currently, first we identified that that was above here our 10th argument, these first 8 bytes. However, now we are writing stuff before that. So these are 9 characters. So 9 characters, that means that these first 8 characters are actually the 10th argument, and that's going to give issues. So let's actually remove this 4 here. So we only have 3 here. This is 8 long now. And now we know that this one is going to be the 11th on the stack. So this is going to be the 11th argument to printf. So we change this 10 to 11, and now we should see that that works nicely. And we see indeed that works. So we print out 1, 2, 3 x at, but we don't see if we actually change this winner value, because we have no way of seeing that yet. And for that, I'm going to use IDA. I think it's a very useful tool to be able to look into the memory and look at what's happening on the stack and stuff like that. So let's edit our script here. So we're going to wait for some input after we've created our payload. During this time, we can go into IDA, we can say debugger attach to process and attach to the Leet test process. So now that we are here, we're going to press play here. We're going to send the payload, and I put a debugger point, a breakpoint, right where it's reading the winner place, the winner location. And what do we see? We see that winner now contains 3 as data. And well, we had 3 characters before that, so we have now been able to overwrite this winner location in memory, because as you can see before in ghidra, we saw that winner contains Cafe Babe. And actually we can put something else here. For example, if I want to say, okay, instead of 1, 2, 3, I can do 4, 5, 6, 7, 8, 9. And I have to make sure that this now all adds up to 16. So wait, that's 8. And then I need to have something like this. That should be 16. And that means that our P64 winner is now going to be the 12th argument to printf. So we need to change that to 12. And this looks all very confusing, but it's really logical if you play around with it and you see how it works. So again, we're going to connect to this in IDA, and now we should see that we have like 13 or like, no, not 13, like 11 in that location, or like something around 11. So let's run that again. Oh, and we had an error, so that likely means that this doesn't add up to 16. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, yeah, that's 1 too many. So if we remove 1, now we should see that we can nicely do this all over again once more. Attach to the process, Leet test. Gonna run that. Continue here. And we see that the winner now contains OB, which is 12. So we can actually control this value in any way we want. What is remaining for us? So now we control, this value is static, we control this value, and this value is still random. So what are we going to look at next? Next up, we're going to be looking at how we can actually also leak this value so that we control all 3 values in this equation, and so that we can actually get past this if and get the flag. So that's coming up right up next. So now we want to print out or like find the address of these random bytes that have been gotten from def urandom. And on the stack, we've already found out that in our printf string, the argument for printf that is going to print out the beginning of this buffer is the 10th one, and local 13c, the one that we want, is actually above there on the stack. So that means that somewhere between the 1st and the 10th argument, our random bytes are, and these random bytes are kind of our secret that we need. So let's see if we can find them. So to do that, we are going to run our Leet test, and as our name, we can say, okay, print out some pointers. And let's see if we can find any. And I accidentally entered some weird characters in there. So let's try that again. Let's just copy these 4 like that. Okay, so the 10th one is here. So somewhere, one of these has to be our secret value. And we know our secret value is going to be 2 bytes. So it's not going to be nil, it's not going to be 3. These are 2 bytes, C2, 2E. So that's a possibility, and none of the other ones are a possibility. So we know that this one is going to be it. And this is actually the 7th one. So we can do 7 and print that out. Cool, perfect. So what I actually did is I put that in a script. So I get this, it's very simple. First step is getting the def random value. And yeah, so we're just taking the 7th position here, we're receiving the line, decoding it, just getting the right location, the right bytes, and then we print that out, and we also store it as an integer, so from base 16, from hex to integer. So let's run that. and we see that we find this random value XEE3, which apparently gives errors. Oh, yeah, that gives errors because this X is still from the OX, so I guess my script doesn't work all the time, which is something that I will fix later, but for now it works often enough for me to be happy, so I'm just gonna leave it at that. So yeah, we have this random value most of the times. Perfect. Now from that we can also calculate a target value. Why? What is our target value? Well, we can override this winner, and this winner is going to what we override that with is going to be our target value, and we are going to be calculating our target value by multiplying those random bytes that we gotten by Leet code. So in my code, you can see that the target value is just this random value that we just got times Leet code. We're going to then log that, and then here I still have my code from earlier where we overwrote the value in winner by the amount of input that we give. Now, looking at the target value here, it's in hex and it's very big. If I go into Python and I turn that into integer, you can see this is larger than trillion. I don't even know how to pronounce a number this big. So in principle, what we would have to do is we would have to output this many bytes to the screen, or output it, and then we could override with that percentage n that we used earlier, we could override the winner by this value, and that's just not possible because this would be impossible to input. So that's a bummer. We can't use that. However, there are very smart ways of getting around that, and that using these length modifiers. So using HH and LL, we can override certain bytes. So we can override like the two lowest ones, the two highest ones, stuff like that. And that's very difficult to do manually. And I think there's also no point in trying it manually, because once you understand how this kind of works with the percentage n, that we can override the value by the number of bytes, then we can kind of use automated tools to do that stuff. So for example, we can use the PwnLib from PwnTools, the format string, bug exploitation tools, and these are very, very, very useful. So I'm going to show you how to use them. So first of all, we have this exec fmt function. So this exec format function, you can name this anything you want, but the idea here is that PwnTools is going to have a way to interact with our program. So all this is going to do is this is going to take a payload. We're going to send that after please enter your name. We're going to send the payload, and we're then going to return the result back. So that way PwnTools knows how to interact with the binary, and we can like supply when to send stuff and when not to send stuff and stuff like that. And that's what we're going to feed into format string, then that function that it's going to use to communicate. And then we supply the offset here. So the offset is the, in this case 10, because we verified earlier when we were doing it manually that at the 10th location, like if you printed out all of these P's, at the 10th location we have the beginning of our buffer on the stack. So that's what this offset is. We are then going to do the next statement, which is f.write. So we're going to write to winner the target value. So the value that we want in winner, we're going to write that. And lastly, we're going to execute the writes. So this is actually this f.write is not going to execute anything, but this execute writes is going to execute them. So let's see what happens if we run that. So I have to exit out of Python and run it, and we see a value error, pack number does not fit within the word size. Why is that? Well, that is because PwnTools has no idea as to what kind of thing we're running here. Are we running 64-bit? Are we running 32-bit? And by default, it's going to assume 32-bit, which is wrong in this case. So we have to supply a context.arch is equal to x86 underscore 64. So now if we save this and run it again, we should see that it doesn't have any problems with running it. And it says come right in, and this is locally, so it's not going to print out the flag because I don't have the flag. But we have passed the if statement, because if you look at the code here, this come right in is after this while loop that we wanted to exit. Great, cool. Let's see if that works on the remote then, shall we? So going to the remote, we can run this again, and we see that we get the flag, and that is great. And now we can also take a look at our format string that it actually ended up being. So as you can see, this is a very, very difficult format string here, but I'm going to try to explain it really shortly. So this first part, 134C, is going to just input that amount of characters. So 134 characters are, I think it takes an argument from the stack and then pads it with until it's 134 in length. And that is then going to be used. 134 is going to be outputted. So this %n here is then going to put 134 at the, and then with LL, those are those length modifiers that I talked about. Is going to put it somewhere. Then next up we have the same idea again, but this time 97 to another location, and that way it chains together a whole bunch of stuff to make sure that the ultimate value in that location in the winner state is that the target value that we wanted. So it's really difficult to make manually, and people have made it automatically, and if you know kind of how it works and what the idea behind it is, then I don't think it is that big of a deal to use automated tools. You have to be always dangerous with automated tools because sometimes people can automate so much and you don't understand what's going on, and that's an issue because you always have to understand what's going on, but once you do, you can use tools. Another thing that I want to mention is here we supplied this offset ourselves, but we can actually get rid of it, and PwnTools will find this offset for us, and it will do so by just trying a whole bunch of things. So, okay, we got that error again. But as you can see, it tried a lot of payloads here, so it tried the first one, the second one, third one, fourth one, and so on. And then when it got to the 10th one, it realized, hey, that's the right one, so it also exploited it that way. So that is also a possibility. However, I prefer finding it manually in some cases. Definitely to explain it in this video, manually was a better decision, but you can also do it automatically. And that was it for this video. I hope you enjoyed this video. This was a different kind of exploit than what we've done before. No buffer overflows here, but it's also an exploit that happens, and this happens a lot due to programming errors. And it's very avoidable, but still sometimes happens, and it's good to know about. I hope you enjoyed this video. I hope you learned something new, and I hope to see you back for another video next week. Take care. Goodbye.